is a very important video in the subject of differential geometry. The concept is called embedding, and it relates to some of the most important and intrinsic concepts of differential geometry, which is embedding, structure preservation, immersion, embedding in R4, and relative concepts. In this video, I will be primarily talking of what is the concept of embedding. I will cite some simple examples of embedding. I will also speak on structure preservation and primarily how we can embed different surfaces in R4, what is basically called a surface and related features, structures and illustrations. So this is a very important concept building video in the area of differential geometry. So if you're looking to study differential geometry further, please watch this video till the end, because embedding and other structures and concepts are very important and central in learning the subject of differential geometry. My name is Shaunak and you're watching this video on my channel Physics for Students, and a warm welcome to watch this video. So first let us look into what are the topics that we are covering today. So primarily, as I told you, we will be talking on the concept of embedding as a definition, what is called structure preservation, embedding examples, how embedding is used in general topology, embedding example with torus, what is a surface, what is meant by orientable and non-orientable surface, and what is surface in terms of formal definition. Before we go ahead, I would just like to make a note that the concept of embedding or other concepts, when I talk to the students, often becomes difficult because there is a problem of visualization. I was just talking to one of the students from Aligarh Muslim University. He was also talking to me regarding the same problem. It is how can we visualize things. So I would be using certain weird non-structural drawings and illustrations which might not be very relevant to differential geometry, but that would give a kind of a picturesque visual idea on the basic concept. So first we are going to talk about the intrinsic description of manifold and what is called an embedding. Okay, so in mathematics, embedding, or sometimes called embedding, is one instance of some mathematical structure contained with another instance, such as a group or that of a subgroup. Now, most important is that when some structure is embedded in another, there is some kind of a structure preservation which is maintained. So let me first take a very simple example to illustrate that. For example, this is a mathematical structure. Now, when I talk that it is a mathematical structure, it can be any structure. It can be even simple addition, multiplication, subtraction. It can be even a field. It can be a topology. It can be anything. Let us imagine this to be a mathematical structure which obeys certain axioms, rules, etc. And we get another mathematical structure which is this one. Okay, so we are trying to embed one mathematical structure into other. So this is how the embedding goes, one part to the other, and we call that some of the properties are preserved. So when some object X is said to be embedded in another object Y, so you can just imagine this one to be X and this one to be Y. So when some object X is said to be embedded in another object Y, the embedding is actually given by some injective and structure preserving map, which is followed by this notation F, where X maps to Y. Now, actually this is shown by this kind of a hook, I would say a hooked arrow, which actually refers to embedding, this one. And this is what is an injective function, nothing new to repeat. You all know what is an injective function. When each of the points of one domain is directly having one particular partner of the other. Okay. So I will just repeat once more. When some object X is said to be embedded in another object Y. Now this object X, just as I told, it is a mathematical structure, is being embedded into another object y on the right hand side. The embedding is given by some injective, you saw the injective function on the right hand side, and structure preserving map, which is given by f, this notation, which is a hooked arrow. So now you can see that each of the objects of one particular mathematical structure will have an injective function, and there will be structure preserving. Now when I talk of structures preserving, it depends on the kind of mathematical structure of which x and y are instances. So in terminology of say for example category theory, a structure preserving map is called morphism. Anyway, the fact that this one it depends on what kind of mathematical structure of which x and y is, and this hook is actually, I just used the latex code, so I just thought to give you an idea that this is how it is written, in order to, if you want to write sometimes on internet or web, so this is the latex code. Anyway, so the concept of structure preserving is actually dependent on what kind of mathematical structure you are talking about or we are talking about. So in category theory we call morphism, then we have homeomorphism, etc. So one structure is getting embedded in another structure where there is an element of structure preserving and injective function. Each of them is pointing to the element of from A to B. Okay, some embedding examples actually would make things much more easier. So for example, if I take this f, it can be basically a field, right? In mathematics, what we field. So if it maps to in a certain space in such a way that the connectivity or the algebraic structures are preserved. So field embedding preserves the algebraic structure, that is plus and minus, that is multiplication and addition. For example, if we take a topological structure T, which is embedded in a topological space, then what it does is that it preserves open sets. Similarly, you can think of a graph embedding preserves a connectivity, and so on. Now, in many cases of interest, there is a standard, I would say, canonical embedding. Like this, for example, this natural numbers is embedded in natural numbers in the integers. The integers can be with the rationals, then the rationals can be further into real numbers, and the real numbers can get into complex numbers. Okay, so these are simple, I would say, kind of an example of embedding. So you see now that natural number, when it is embedded into integer, integer embedded into rational, but not the other way round. So the structure has been preserved, while here's all the elements of the natural number as an injective function which follows with that of the integers. So for example, the real numbers, the complex numbers, and now in such cases I can say that it is a domain. It is common to identify that this the domain of x, which we call with its image of x, is contained in so y, so that this one is true. This is simple, right? So to the domain of x with its image f of x y contains, so that f of x is this. Okay, so this clears the concept of embedding. However, I would like to take one more example, that is in general topology, and embedding is basically a homeomorphism on its image, onto its image. Okay, now if you are listening the video for the first time and you really do not know the term homeomorphism, please go to my playlist of differential geometry. You will find an exclusive video which is called homomorphism, homeomorphism and isomorphism. You can go to that video to check out further details on what is homeomorphism. So what we are trying to tell is that if we get an injective continuous map, remember that the map has to be injective and it has to be continuous between, say for example, two topological spaces. Here I have just mentioned them x and y. I mentioned it in box just to give you a better visualization. So an injective continuous map F maps X to Y, and it belongs to topological spaces X and Y. Now it is a topological embedding. We are talking, remember, in general topology. It is called a topological embedding if there is a condition. What is the condition? If F yields a homeomorphism between X and F of X, where we can say that this is true, that the homeomorphism exists. This one is taken as a subspace of Y. I'm going to say X is treated as a subspace of Y. So this actually is the definition of embedding in general topology. An injective continuous map between two topological spaces X and Y is a topological embedding. When it happens, if F yields a homeomorphism between X and F of X, where we should consider that F of X carries the subspace of topology, that's a subspace of Y. So what we can tell is that intuitively, because this X is treated as a subspace of Y, most important is that every embedding is injective. Yeah, every map that is injective, continuous, and either open or closed can be termed as an embedding. So this is I can say a nutshell, very important. Every map that is injective, continuous, and either open or closed is an embedding. However, there is also embeddings which are neither open nor closed. We are not taking those into account. It can be topological invariant, those things we are not taking. Now, injective, you know what it is. Continuous also you know. Either open or closed is also what you know. You can do one thing. You can go to my previous videos in topology, which I just made. Open, closed set, open ball, closed ball, everything I have discussed. Okay, now this figure that you are looking into sometimes seems to be quite complicated, right? So this is basically a one-dimensional manifold. Okay, it is you can imagine just is to be a closed curve, that is, it is a closed circle. Now you see the problem of distinguishing embeddings of a circle in R3 is one of the goals of knot theory, which carries with deep difficult areas of mathematics. What I'm trying to make a point over here is that this simple one-dimensional manifold, which is a kind of a closed circle, complications disappear if we try to take them into higher dimensions. If you are really interested in physics, not talking of differential geometry, you can go to my playlist on string theory, where I have explained why string theory requires additional dimensions. It is something analogous to what today we are speaking. So if we want to identify this kind of a manifold, right, the problem of I would say embeddings are much more easier in a circle of R3 if you're trying to take it in higher dimensions. For example, all these knots can be disentangled, that means this can be opened up inside R4 with R3 viewed as a subspace. So the knots in these become somehow like this, and they become unknots, right? That means the problem disappears if we take that simple one-dimensional manifold into higher dimensions, and we can disentangle these knots into R4, right, with R3, which can be viewed as a subspace, and R4 then become the unknots. So this is just an example to show you that sometimes things which appears to be so simple are difficult to express in terms of embedding, but becomes easier when we take it for the higher dimension. So here it is, the intrinsic description is sometimes much simpler to deal with than the extrinsic one. So that is why I mentioned the heading right at the beginning, that intrinsic definition of manifolds, because we are dealing with intrinsic definitions. Okay, so for example, we could take a torus, right, and we know this is this one, right, of R3. It is not specially, if you want to again, if you want to describe it in terms of mathematics, is not always very simple. But once we introduce this kind of a parameterization and polar coordinates, etc., you see, so where theta and phi, this theta and this phi, are determined by multiples of 2 pi, what we get is that this T2 is simply a product of two circles, I would say, yeah. So S1 and S1. That means T2 or the torus is considered of ordered pairs of points on the circle where the two factors are basically theta and phi. Now what I am trying to make a point over here is that this torus, when we are trying to embed it or when we are trying to parameterize it, it becomes quite easier to determine rather than just with the equation or just with the set that we it consists of. Okay, so here this is a 2 torus, right? It is a 2 torus. It is called genus 2. So it is also depicted as a surface of revolution. Now if you are given 2 torus or 2, so it is defined as the product of two circles. We have seen that S1 and S2. Now given this kind of a surface, the torus, this portion, right, and given real numbers small r and big R, right, this is from the pipe, and this is right, the big R is basically the radius central from the center. So if you're given in Cartesian coordinate, the equation looks like this, and now if you're given real numbers where 0 is less than R is less than big R, then what we get is that here it is, then we get that if we take a radius in this R in the xz plane with center R at 0 and we rotate around the z axis, then specifically what we get, the resulting equation is this. And you can see here x, y and z, these are basically rotations in terms of the axis. So what I am trying to show you over here is that this is an example where we have taken small r and big R. Now you might be thinking that why I have taken this, it will soon become clear. Now just remember or take a note of this equation right at the middle, rotating along the z axis, what we get. So what we can say is that this equation, in contrast to the coming equation and this equation, in contrast, you will see that there is no distinction between the small circle of radius and large circle that is the radius R, capital R. So there is no distinction between small circle of radius small r and large circle of radius capital R. So what, so it is just this. So because there is no distinction between this and this, what we can say is that the new description suggests that embedding of R, this T2 into R4 is much, I would say, beautiful, much better than in R3, and the triple torus also can be embedded into R3. Okay, so the basic idea of this part is basically that when we are comparing these two equations, one with parameterized form and that with a non-parameterized form, so the parameterized form has the small r and big R, whereas the non-parameterized form, this T2, doesn't have. There is a utility that this R torus can be embedded into R4 and it can be also embedded in R3, and we have seen earlier also that if you take it to higher dimensions, the embedding becomes much easier. Okay, so these embedding, what are those which are embedded? Obviously these are surfaces. We will try to give a very easy and kind of a mathematical description of surfaces, although surfaces are a huge subject to deal with. However, we will try to give a clear idea. Okay, so first of all, I would try to give you a very generic definition which is quite easy to understand. So our surface is the same thing as a two-dimensional manifold, right? So we have already encountered some examples of surfaces. For example, there's a torus, there's a sphere, and a double torus, or might be triple torus, etc. Now all these are orientable surfaces. Orientable means that they have two sides where you might paint in two different colors. I have spoken at length using Mobius strip and non-orientable surfaces in my last video on topology, not differential geometry. You can go over and there have a look. So this is something, a clear definition of orientability surfaces that allows a consistent definition of clockwise and counterclockwise. So it turns out that these are all the orientable surface if we consider the surface intrinsically and only consider surfaces that are compact. I mean to say those which are not going up to infinity, then they do not have a boundary. So for instance, for example, this one, the Klein bottle, famous Klein bottle, is an example of a non-orientable surface. What is non-orientable surface? If an ant moves along this part, the entire directrix is changed as it comes down. You can just have a look into my previous video in differential geometry also, which I just published a week back, and I have spoken about orientable and non-orientable surfaces. So what it comes clear is that the more, by attaching handles, just like we can think of torus, double torus, etc., we get a kind of a non-orientable surface. But we have missed what is in some sense the simplest, I would say, non-orientable surfaces. Ironically, it is a surface which is very hard to realize in three-dimensional space. It is called a projective plane. So in mathematics, the projective plane is an example of a contact non-orientable two-dimensional surface, in other words, which has got a one-sided surface. Now it cannot be embedded in standard because it intersects each other. Okay, now here I would like to give you a wonderful kind of a idea, and rather I would suggest you to go there and see it. This projective plane, because it is a non-orientable surface, this plane is often described topologically in terms of construction. So in terms of construction, I mean to say based on a Mobius strip. So Mobius strip, I would say if you could glue the single edge of the Mobius strip to itself to the correct direction, you will get a projective plane, right? But this cannot be done in three-dimensional space, right? Similarly, gluing a disk along the boundary of the Mobius strip gives back to a projective plane, and topologically it has the Euler characteristic 1, and hence it is called a demi-genus. Okay, so in order to say all those things, it seems to be quite weird, and again visualization is a problem. So what I have done is that I have taken this person's I cannot show it because you understand YouTube has got certain restrictions. So real projective plane and minus disk is a Mobius strip, and you should go to Joe's Lays this particular animation, and I will give the animation over here, right? It is basically how a real projective plane becomes a disk, and that disk results in a Mobius strip. It's an absolutely great, wonderful animation, and I would really suggest you go there and see this animation. Although Joe's Lays, most of our videos are called visual mathematics, you'll find a lot of animations on topology and differential geometry. However, this animation will give you a clear idea that how a projective plane can be built up from first it would show a sphere, then it would slice into a disk. From that disk, it will give rise to a Mobius strip, and so on. So just a few minutes of animation. Joe's Lays, I've given the description, in the description, the link to this animation. you must watch it. So to define, I would say in a way, in a strict manner, a surface is basically a subset of R3, obviously, that looks like R2. That means normal Euclidean space. Formally, we can define as this a subset S of R3. So imagine a subset S of 3 dimension, right, is a surface. If there are every point P, there are small points over, right, which are elements of S, that is a subset. There is an open set U, which is in R2, that is 2 dimension, and an open set W on R3, such that the subset S intersects with the open set W, and it is obviously homeomorphic to U. So a subset of a surface S is in the form S intersects W. The W is an open subset in R3. It's also called an open set of S. This is the kind of a strict definition of what is a surface. Okay, the next part, which is comes in differential geometry, is called what is an immersion. In immersion is a differentiable function between differentiable manifolds whose differentials is everywhere injected. So the geometry of immersed manifolds are basically nothing but generalization of the very old classical differential geometry of surfaces in the R3 Euclidean space, and this is written as this. Now immersion itself requires another video, so I won't be explaining immersion over here. I would take another video to make more about immersion and talk about the distinction or the similarity difference between immersion and embedding, but this is just for the sake to know. Don't worry if you don't understand this notation. I will be taking it forward in the next video. So in the next video, I am targeting to complete immersion and the related concepts, but this video is something which primarily speaks of surfaces and embedding. I think that I have been able to give you a much more illustrative example rather than a strict mathematical definition, because that is very important to visualize concepts. That completes our today's video. Thank you for watching it. Please do subscribe to my channel Physics for Students, like and put up your comments. How did you like today's video? And I will wait for your comments, and I will wait for your reactions also. I will be back very soon with another video, and this series of differential geometry will carry on as usual. Stay safe, eat healthy, think healthy, continue learning mathematics and physics, and be at the top of the world. Thank you very much for watching this video. Goodbye until next time.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.